Hey, so hello everyone. My name is Donna and I'm a recent master's graduate from Material Science program from the University of Ontario Institute of Technology. So today we're going to go over some commonly asked chemistry questions at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. Now let's just get started on our set of questions for today's session. Okay. So question 1 is to calculate the molar mass of sodium hydroxide and the molar concentration of a solution containing 4.273 grams of sodium hydroxide in 850 milliliters. So first we need to calculate the molar mass of sodium hydroxide, and we need all the individual atomic masses of the elements involved in this compound. And we can just find these values on the periodic table. So the molar mass of sodium is 22.99 grams per mole. The molar mass of oxygen is around 16 grams per mole. And the molar mass of hydrogen, 1.01 grams per mole. So if we add all these values up, we get around 40 grams per mole. So this was part A of this question, and part B wants us to calculate the molar concentration of a solution containing 4.273 grams in 850 milliliters. So first, we need to find out the number of moles in this amount of sodium hydroxide. So we have 4.273 grams, and we just need to divide by our molar mass, which is 40 grams per mole. And for the number of moles, we end up with around 0.106 moles of sodium hydroxide. So now that we have the number of moles, we can calculate concentration by using the formula number of moles over volume. So we calculated our number of moles, and we just need to convert our volume to liters. So 850 milliliters, if we divide by 1,000, since there are 1,000 milliliters in 1 liter, we can convert to liters. So now we end up with a concentration of 0.125 moles per liter. Okay, so let's see what the junior tutor said. They found the molar mass of sodium hydroxide, which was 40 grams per mole. They calculated the number of moles, which is 0.106, and then their concentration was also around 0.125 moles per liter. So the solution is correct. Okay, so question number 2. Is acetone polar or nonpolar, and will sodium chloride dissolve in it? Okay, so we have the Lewis structure of acetone, which can also be known as propanone. So it's a 3-carbon chain with a ketone on our second carbon, and we kind of get something like this. So to find out whether or not acetone is polar or nonpolar, we need to calculate the electronegativity differences between carbon and oxygen and carbon and hydrogen. So first let's do carbon and oxygen and look up their electronegativity values. Okay, so oxygen has an electronegativity of 3.5 and carbon has an electronegativity of 2.5. So the difference between the two is 1. So therefore this bond is polar, and we know that because the electronegativity difference is greater than 0.4, but it's less than 1.69. Okay, so now let's calculate the electronegativity difference of a carbon and hydrogen bond. So carbon's electronegativity is 2.5 and hydrogen's is 2.1. So their difference is only 0.4, so the carbon-hydrogen bond is nonpolar. So I can show a dipole moment kind of going towards the direction of the oxygen, because since oxygen is much more electronegative, there's going to be an uneven distribution of electrons. So I'm just going to write up here that we have a non-zero dipole moment. So therefore, this molecule is polar. So, since like dissolves like, it will dissolve in sodium chloride, since sodium chloride is also polar. Okay, so we can kind of sketch out what this looks like. So because the oxygen is more electronegative, it makes acetone have partially positive and partially negative sides. So if we had a sodium chloride salt, we know that an ionic bond is formed between the sodium and the chlorine. But this positive sodium ion can be attracted to the partially negative oxygen on our acetone, and this is how they can dissolve together. Okay, so the junior tutor said that the bond between the carbon and oxygen has a separation of charge due to electronegativity difference. Its structure does not also cause the cancellation of the dipole moment, thus acetone is a polar molecule. Sodium chloride has an ionic bond, which is a very strong bond. Acetone, which is not that strong as a polar molecule, cannot be able to dissolve sodium chloride since it cannot overcome the energy required for an ionic bond to break. Okay, so sodium chloride is polar as well, so they will be able to dissolve. I'm just going to say that since acetone is a polar molecule, it is still able to dissolve NaCl since all ionic compounds are considered polar. Okay, so question number 3. What is the formula for ammonium sulfide? So sulfide can be spelled with a PH or with an F. And if we break apart this ionic compound name into its separate ions, ammonium is a polyatomic ion that is NH4+, and sulfur is just a gas, and its oxidation state is -2. So to find out the formula of ammonium sulfide, we have ammonium, which has a +1 charge, and sulfur, which has a 2- charge. So therefore, we need 2 atoms of ammonia to neutralize sulfur's -2 charge. So we put ammonia in brackets, and we need 2 of them, and the sulfur will just stay as S. Okay, so let's see what the junior tutor said. Ammonium sulfide is an ionic compound made up of the ammonium ion and the sulfide ion. Structure of ammonium is NH4+, and the structure of sulfide is S2-. And since the total charge must be 0, it means that there are 2 ions of ammonium needed to neutralize the charge on the sulfide. Okay, so they got the same answer. So this solution is correct. Okay, so question number 4. Why do we believe that the valence electron of calcium and potassium resides in the 4s orbital rather than in the 3d orbital? Okay, so to answer this question, let's first find the electron configurations of both calcium and potassium. So to find the electron configurations, we need to divide our periodic table into the different orbitals, s, p, d, and f. So after dividing it, we get something like this. So the s orbital are the first 2 columns here, including the helium. And the p orbital is this green section. The d orbital are the middle transition metals. And the f orbital is just the last 2 rows, the lactanides and actinides. So calcium is found here. Atomic number is 20. And if we start from hydrogen and move left to right across the periodic table, we need to write the row number followed by the block letter. And in the superscripts, we can show how many electrons are in each orbital. So starting from hydrogen, we write 1s, and there are 2 electrons in the 1s orbital, so we put a superscript of 2. And then down to the next row, we have 2s, 2. And then when we get to 2p, this orbital is able to hold 6 electrons, so we can put 2p6. Down to the next row is 3s2, and then 3p6. And then calcium is in the 4s orbital, and it'll just be 4s2. And you can see that potassium is right beside it. So we can also just write similar electron configuration, except it'll end in 4s1. Okay, so the question asks, why do we believe that their valence electrons resides in the 4s instead of the 3d? So this is because their 4s orbitals are lower in energy. So typically for transition metals, sometimes your 4s can be lower than the 3d orbital. But for both calcium and potassium, the 4s orbitals would still be considered lower in energy. Okay, so the junior tutor said that from the Aufbau principle, electrons fail in order of increasing energy in the orbitals. sp, d, and f are also part of the increasing energy as f goes to p, to d, up to f shell, which is the highest among the four. In the case of transition between 3d and 4s, the diagram for their energy level is that 4s is somewhat lower in energy than with the 3d orbitals. Thus, this made the electrons fill up the 4s orbital first before 3d. Yep. So this solution is correct. Okay, so question number 5 says to consider the equation for the reaction of sodium and nitrogen to form sodium nitride. So we have 6 sodium plus nitrogen gas produces 2 moles of sodium nitride. For part A, if 81 grams of sodium is mixed with 27 grams of nitrogen, what mass of sodium nitride forms? Okay, so first let's find the number of moles for both of these reactants to see which one is the limiting reagent. So calculate for number of moles, it's going to be the mass over the molar mass. So we know the mass of sodium was 81 grams, and the molar mass of sodium we can find on the periodic table. It's 22.99 grams per mole. So therefore, the number of moles for sodium, let's calculate it. Is equal to 3.52 moles. And let's do the same thing for diatomic nitrogen on this side. We have 27 grams of N2, and the molar mass of a single nitrogen atom is around 14. So if we have 2 nitrogens, it's around 28 grams per mole. So its number of moles is around 0.96. But it doesn't end there because we need to find out how much sodium nitride is formed with these amounts of moles for our reactants. So starting with the nitrogen, we have 3.52, the sodium, moles of sodium, and we need to multiply by the molar ratio to find out the mass of sodium nitride that can form with this amount of moles. So using our balanced equation, we can see that we need 6 moles of sodium to produce the 2 moles of sodium nitride. So let's just write down the molar ratio. And we can calculate this number of moles. So this is times 2 divided by 6. You get around 1.17 moles of sodium nitride formed. And let's do the same thing for the nitrogen. So we have 0.96 moles of nitrogen, and we only need 1 mole to form 2 moles of sodium nitride are formed with only 1 mole of nitrogen gas. So we just need to multiply 0.96 by 2, and we get 1.92 moles. So therefore, we can say that sodium is our limiting reagent. Okay, so now that we know the number of moles that can be formed, we can calculate for the mass of sodium nitride. But first, we need to find out its molar mass. So sodium nitride, its molar mass is 3 times the molar mass of sodium plus the molar mass of nitrogen. So sodium's molar mass is 22.99 and nitrogen's is around 14.01. So if we add these values up, we get a molar mass of around 82.98 grams per mole. So to calculate for the mass, we just need to multiply our molar mass by our number of moles that we found in the previous step. So 82.98 grams per mole multiplied by 1.17 moles gives us around 97.09 grams of sodium nitride. Okay, so part 2 says if the reaction in part B has a yield of 75%, how much sodium nitride is actually produced? So we just need to multiply our expected value by 0.75. To find 75% of our expected value. So that means we actually produced 72.8 grams of sodium nitride. Okay, so let's see what the junior tutor said. They first found the number of moles of each sodium and nitrogen, and then they found the limiting reagent. and deduced that sodium was the limiting reagent. Okay, so now when they use the limiting reagent for stoichiometric calculations and found that 1.17 moles of sodium nitride is formed. They converted this to grams and got around 97 and multiplied that by 0.75 and also got around 73 grams produced. So the solution is correct. Okay, so question number 6. What is the Bronsted-Lowry acid and base? Okay, so first, a Bronsted-Lowry acid. This is known as a proton donor. And a Bronsted-Lowry base is the opposite. It is a proton acceptor. Okay, so let's have an example. Let's say we had hydrochloric acid plus water produces H3O plus Cl minus. And so H3O plus is the hydronium ion. So in this case, hydrochloric acid donates one of its protons to water. So this makes hydrochloric acid our Bronsted-Lowry acid. And since water accepted the proton, this becomes our Bronsted-Lowry base. And our products, which is the hydronium ion and chlorine ion, our H3O plus becomes our new conjugate acid, and the chlorine minus is referred to as the conjugate base. So the reason why they are conjugate acids and bases is because if we were to reverse this reaction, then the H3O plus becomes the proton donor and the chlorine minus becomes the proton acceptor to form HCl and water. Okay, so the junior tutor said that the Bronsted-Lowry theory relates the interactions in acids and bases in terms of proton transfer between chemical species. A Bronsted-Lowry base accepts the proton in the form of hydrogen ion, H+, and the acids donate the proton in the form of hydrogen ion. So they show a conjugate acid-base pair which consists of two substances that only differs by the presence of a proton. Conjugate acid is formed when a proton is added to a base, and a conjugate acid has one more hydrogen plus atom and one more positive charge than the base that formed it. And the conjugate base is a substance that is formed when a proton is removed from an acid. The conjugate base has one less proton and one more negative charge than the acid that formed it. And then they also showed a general expression. So the solution is correct. Okay, so question number 7 is to determine the molar mass of sodium carbonate, which is Na2 CO3. So to find the molar mass of sodium carbonate, we would need all the individual molar masses of the atoms involved in this compound. So these are values that you can just find on your periodic table. And to find the total molar mass, we need to add up their individual atomic masses and also take into account how many of each atom there are in the compound. So for sodium, it's going to be 2 times the molar mass of sodium plus the molar mass of carbon plus 3 times the molar mass of oxygen. So sodium's molar mass is 22.99 grams per mole. Carbon's molar mass is 12.01 grams per mole. And lastly, oxygen's molar mass is around 16 grams per mole. So now when we add all these values up, we get around 105.99 grams per mole. Okay, so the junior tutor said that sodium carbonate is the chemical formula, and an ionic compound commonly referred to as washing soda. It is used in cleaning products, glass production as a food additive, and more. Molar mass refers to the total mass of 1 mole of that substance, and in this case, aluminum acetate. I think they mean sodium carbonate. So to calculate the molar mass, they need to know the atomic masses of each element, and they got it from the periodic table, and then multiply the standard atomic mass of each to their corresponding number of atoms. Okay, so they summed up all the math and also got around 105.99 grams per mole. So this solution is correct. Okay, so question number 8 asks for the chemical equation for cellular respiration. So for cellular respiration, this is a biological process where our cells break down molecules for energy. So by molecules, we mean like glucose or like sugar. So typically, glucose reacts with oxygen to form water plus carbon dioxide. And during this process, ATP is formed as well. So I'm just going to add here ATP is formed, and this is our source of energy. So if we wanted to write this equation in terms of their chemical formulas, glucose is C6H12O6, oxygen is O2, water we all know is H2O, and carbon dioxide is CO2. So now let's try to balance out this equation. So let's balance out the carbon first. So there are 6 atoms of carbon on our reactant side, and there's only 1 on our product side. So we need to put a coefficient of 6 in front of CO2. And now let's balance out our hydrogens. There are 12 hydrogens on our reactant side and only 2 on our product side. So then we're going to add a coefficient of 6 in front of that as well. And now notice that the number of oxygens on our product side is 12 plus 6, so 18. And we only have 8 on our reactant side. So if we put another 6 in front of O2, then that should make our equation balanced. So this is the chemical equation for cellular respiration. And the junior tutor said that cellular respiration is a biological process in which cells break down molecules for energy. In this process, one glucose molecule reacts with 6 molecules of gaseous oxygen to produce energy in the form of ATP, 6 molecules of carbon dioxide, 6 molecules of water. Carbon dioxide and water are the byproducts of the reaction. So to briefly explain the process, glucose from the food we eat and oxygen from the air we breathe in are broken down in the body to produce energy. Carbon dioxide we breathe out, and water we urinate or sweat out. So therefore, the overall chemical equation balanced for cellular respiration is as follows. C6H12O6, which is glucose, plus 6O2 makes 6 carbon dioxide plus 6 water plus ATP. And in simple terms, the equation can also be expressed as glucose plus oxygen forms carbon dioxide plus water plus energy. Yep, so the solution is correct. Okay, so those are all the questions for this session. And if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. And if you'd like to submit a question of your own, then check out the links in the description. And also, if you enjoyed today's video, you can give it a thumbs up and a comment, or you can share with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.